Here's a quick look at what we'll cover today. We'll start with a brief introduction to PFAS and their environmental and health concerns. Then, we'll look at existing treatment methods and why activated carbon stands out. After that, we'll dive into how activated carbon works, the types of carbon materials available, and review real-world data from PFAS removal projects. Finally, we'll discuss ongoing challenges and look ahead at future innovations. PFAS, or per- and polyfluoroalkyl substances, are a large group of synthetic chemicals used since the 1940s in a wide range of consumer and industrial applications. Their defining feature is the presence of carbon-fluorine bonds, which are among the strongest in organic chemistry, making PFAS highly resistant to heat, water, and degradation. As shown here, PFOA and PFOS are two of the most studied PFAS compounds. They both have a hydrophobic carbon-fluorine tail and a hydrophilic head group, PFOA with a carboxylic acid group, and PFOS with a sulfonic acid group. This structure gives PFAS their unique properties but also contributes to their persistence in the environment and in the human body. Due to their stability, PFAS are often referred to as forever chemicals, and their widespread use has raised growing concerns about their long-term impact on ecosystems and health. Gen X is a newer generation of PFAS chemicals developed as a replacement for the widely phased-out compound PFOA. Chemically, Gen X is the trade name for hexafluoropropene oxide dimer acid and its ammonium salt. Compared to legacy PFAS like PFOA and PFOS, Gen X has a shorter fluorinated carbon chain, which was intended to reduce persistence and toxicity. However, Gen X still exhibits environmental persistence and can accumulate in water bodies, posing challenges for water treatment facilities. Because of its shorter chain, Gen X behaves differently during adsorption processes, often making traditional activated carbon less effective. Regulatory agencies worldwide are beginning to recognize Gen X as an emerging contaminant, leading to increasing monitoring and new guidelines. Understanding Gen X's unique chemical structure and environmental behavior is essential for designing effective removal technologies. PFAS are often referred to as forever chemicals because of their extraordinary resistance to natural degradation. In the environment, they persist for decades, spreading through soil, rivers, and groundwater. Once released, they can travel long distances and accumulate in plants, animals, and sediments, eventually entering the human food chain. These compounds have been detected globally, including in rainwater, drinking water, and even in remote regions like the Arctic. From a health perspective, PFAS exposure has been linked to a range of serious conditions. Studies have associated PFAS with kidney and testicular cancers, thyroid disease, liver damage, immune suppression, and developmental issues in children. Because of their widespread use and persistence, nearly everyone has some level of PFAS in their blood today. Drinking water is considered one of the most significant exposure routes, making effective removal technologies more important than ever. A variety of technologies have been developed to remove PFAS from water, each with different strengths and limitations. Granular activated carbon is widely used and performs well for long-chain PFAS like PFOA and PFOS, but is less effective against newer, short-chain compounds such as Gen X. Ion exchange resins offer moderate to high removal, but can suffer from competition with other ions in the water. Membrane-based processes like reverse osmosis and nanofiltration provide high rejection rates but are costly and generate concentrated waste streams. Oxidation processes and thermal destruction are less commonly used due to limited efficiency or high operational costs. As a result, many treatment systems rely on a combination of methods to achieve regulatory targets. Among all of them, activated carbon remains one of the most commonly deployed first-line solutions due to its availability, cost-effectiveness, and simplicity. Activated carbon is one of the most widely used materials for PFAS removal, particularly for long-chain compounds like PFOA and PFOS. Its porous structure offers a large surface area for adsorption, and it's available in different formats, such as granular and powdered forms, depending on application scale. Activated carbon is cost-effective, requires no energy input, and is relatively simple to operate, making it a practical solution for both municipal and industrial systems. However, it's important to note that carbon performs less effectively for short-chain PFAS such as Gen X. These compounds are more water-soluble and don't bind as strongly to carbon surfaces. Additionally, the presence of other organic matter in the water can reduce adsorption efficiency. Despite these limitations, activated carbon remains a cornerstone technology in PFAS treatment, especially when properly selected and maintained. The adsorption of PFAS onto activated carbon primarily relies on two key mechanisms: hydrophobic interaction and electrostatic attraction. The long perfluorinated carbon tail of PFAS is highly hydrophobic and chemically stable. It is naturally drawn into the nonpolar pore walls of activated carbon by van der Waals forces and hydrophobic affinity. On the other end, the acidic head group, typically a carboxylic acid or sulfonic acid, dissociates in water to form negatively charged functional groups. These anionic sites can interact with positively charged sites on the carbon surface, especially under low to neutral pH conditions. The combined effect of these interactions helps retain PFAS within the pores of the carbon structure. However, the strength of adsorption varies based on the PFAS chain length, pore size distribution of the carbon, and competing organic matter in the water. Understanding this mechanism is essential for selecting the right carbon and predicting its breakthrough performance. In PFAS treatment, three major types of activated carbon are used: powdered activated carbon, regular granular activated carbon, and reagglomerated crushed GAC. PAC offers fast kinetics but limited lifespan and is typically used in short-term or batch processes. Regular GAC consists of crushed irregular particles. It is effective for long-chain PFAS but may suffer from variable performance and attrition. The most advanced option is reagglomerated GAC, produced by compressing fine carbon powder, thermally activating it, and crushing into uniform granules. This material offers high mechanical durability, better pore control, and more predictable breakthrough behavior, making it ideal for drinking water applications and long-term use. Its combination of adsorption performance and system stability makes it the preferred choice for PFAS removal in many full-scale systems. Several key factors influence the effectiveness of PFAS adsorption on activated carbon, both from the molecule side and the water matrix. The chain length of the PFAS molecule is one of the most important. Longer chain compounds like PFOS and PFOA are more easily captured, while short chain PFAS, such as Gen X or PFBA, are more difficult to remove. The functional head group also matters. Carboxylic acids tend to adsorb more readily than sulfonic acids, though this can vary by pH and carbon surface chemistry. Water chemistry plays a large role. Natural organic matter competes with PFAS for adsorption sites and reduces efficiency. The solution pH affects both carbon surface charge and PFAS ionization. Neutral pH generally yields better results. Operational factors such as contact time and pre-treatment also significantly impact performance. Longer contact time allows for better diffusion into micropores, while upstream filtration helps protect carbon from fouling. This chart summarizes the relative impact of each major factor on PFAS adsorption performance. As you can see, chain length exerts the greatest influence. Long-chain PFAS are significantly easier to adsorb. Following that, pre-treatment and head group chemistry also have a strong effect. Removing competing organic matter before carbon treatment helps ensure more available adsorption sites. Solution pH and contact time are also important. Operating at neutral pH and allowing sufficient residence time in the carbon bed both help enhance performance, while factors like natural organic matter and ionic strength are harder to control. Recognizing their impact is critical for optimizing carbon selection and system design. Together, these variables determine how well PFAS can be captured, and for how long before breakthrough occurs. Activated carbon has a finite capacity to adsorb PFAS. Over time, the adsorption sites become saturated, leading to breakthrough when PFAS begins to appear in the treated water. The breakthrough curve, typically S-shaped, illustrates how effluent concentration increases relative to the influent. A common definition is the 10% breakthrough point, where the effluent reaches 10% of the incoming PFAS level. Several factors influence this curve: carbon type, PFAS chain length, flow rate, and EBCT. Short-chain PFAS generally break through earlier due to weaker adsorption. Monitoring breakthrough helps utilities determine the optimal time to replace or regenerate carbon. Delaying this may lead to regulatory exceedance or public health risks. Therefore, understanding breakthrough behavior is critical for designing and operating reliable PFAS removal systems. Understanding when and how often to replace activated carbon in PFAS treatment systems is essential for both performance and cost planning. The process starts with Step 1. Identifying the PFAS contaminants. This involves analyzing the influent water for PFAS concentration and chain length. Long-chain PFAS such as PFOS and PFOA are easier to remove, while short-chain compounds like PFBA or Gen X are more difficult and break through earlier. In Step 2, we select the appropriate type of carbon. Depending on system design, this could be powdered carbon, standard granular carbon, or reagglomerated GAC. Factors like pore size distribution, surface area, and mechanical strength must be considered, especially for long-term treatment. Step 3 is about defining the system's operating parameters, such as EBCT, the empty bed contact time, usually between 10 to 20 minutes, along with flow rate and whether a lead leg column setup is used. In Step 4, we estimate the breakthrough volume, measured in bed volumes or BVs. This refers to the amount of water that can be treated before PFAS begins to appear in the effluent. Depending on PFAS type and carbon quality, this number may range from a few thousand to over 100,000 BVs. Finally, Step 5, calculating the replacement interval. Using the estimated BVs, the EBCT, and the daily flow rate, we can calculate how many days the carbon can be used before it needs to be replaced. For example, with 50,000 BVs, an EBCT of 15 minutes, and a daily flow of 2,000 cubic meters, the expected service life would be approximately 520 days. This step-by-step approach helps ensure proper carbon selection, reliable system performance, and predictable maintenance schedules in real-world PFAS treatment applications. This slide presents the key conditions used in our rapid small-scale column test designed for evaluating PFAS removal by activated carbon. The experiment simulates full-scale behavior with a controlled flow rate of 6 milliliters per minute, targeting a simulated EBCT of 15 minutes. The influent water contains 200 parts per trillion of each PFAS compound, with a background TOC of 0.2 parts per million to minimize adsorption competition. The system runs at room temperature, around 23 degrees Celsius. The column is made of acrylic, with a 2.5 cm inner diameter and 20 cm bed depth, packed with 12 times 40 mesh reagglomerated carbon. All feed water is pre-filtered through a 0.45 micrometer membrane to eliminate particulate interference. The PFAS evaluated includes 6 compounds with varied carbon chain lengths and functional groups, ranging from short-chain PFBA to long-chain PFOS and PFOA. These differences are critical in determining breakthrough behavior and adsorption efficiency. This graph illustrates the breakthrough curves of 6 representative PFAS compounds during the RSSCT experiment. On the vertical axis is the effluent concentration in parts per trillion, while the horizontal axis shows the number of simulated days. Each line represents a different PFAS with varying chain lengths and functional groups. As expected, the shorter chain compounds, such as PFBA, break through the carbon bed more rapidly, reaching near influent levels in under 100 days. In contrast, longer chain compounds like PFOA and PFOS exhibit stronger adsorption and slower breakthrough, extending well beyond 200 days. These trends highlight the chain length dependency of PFAS adsorption, reinforcing the need to tailor activated carbon selection and replacement schedules based on PFAS profiles in the source water. This slide outlines the experimental conditions for the GAC comparison. The carbons compared included reagglomerated bituminous coal GAC, coconut shell-based GAC, and directly activated GAC, ensuring that observed performance differences are attributed solely to the carbon type. This slide illustrates the adsorption behavior of PFHXA across 3 types of activated carbon. The y-axis shows PFHXA effluent concentration in PPT, and the x-axis represents simulated operational days. As a shorter chain carboxylic acid PFAS, PFHXA has weaker adsorption affinity compared to longer chain compounds such as PFOA or PFOS. Consequently, breakthrough occurs much earlier across all 3 carbons. Reagglomerated coal-based GAC still provides the best overall performance, delaying breakthrough the most, while directly activated carbon shows intermediate results. Coconut shell carbon again performs the poorest, with rapid breakthrough and higher effluent concentrations. These findings emphasize the challenge of removing short-chain PFAS like PFHXA, as their higher solubility and reduced hydrophobic interactions significantly lower adsorption capacity, regardless of the carbon type. The reagglomerated carbon typically shows the slowest rise in effluent PFBS concentration. It reaches the 10% and 50% breakthrough later than the other 2, indicating better combination of pore structure and mechanical stability for sustained adsorption. Directly activated carbon often performs well for long-chain, highly hydrophobic compounds due to its microporous structure. For PFBS, which is a short-chain sulfonate, directly activated carbon may show moderate early uptake but a faster approach to breakthrough compared to reagglomerated carbon. Coconut shell activated carbon may show variable behavior depending on manufacture and pore distribution. It can have good initial removal, but sometimes a steeper breakthrough if mesopore volume is limited or if surface chemistry is less favorable. Mechanistically, differences are explained by pore size distribution, which micropores retain small, strongly adsorbing molecules. Mesopores enhance kinetics, surface functional groups, and surface charge that affects electrostatic interactions with PFBS head group, and particle strength or attrition that affects hydraulic performance. Key operational implications: choose reagglomerated GAC for longer lifetime and predictable breakthrough. Consider directly activated carbon if your profile includes many long-chain PFAS, and always verify with rapid small-scale column test before scale-up. This slide shows the adsorption performance of 3 different types of activated carbon for PFOA removal. On the y-axis, we have the PFOA effluent concentration in ppt, and on the x-axis, the simulated operating days. As the curves indicate, reagglomerated coal-based carbon performs the best, maintaining lower effluent concentrations and achieving the latest breakthrough. Directly activated carbon shows moderate performance, with earlier breakthrough compared to reagglomerated carbon. Coconut shell-based carbon exhibits the weakest adsorption, with the earliest breakthrough and the fastest rise in effluent concentration. These results clearly demonstrate that the choice of carbon type plays a critical role in the treatment of PFOA. Reagglomerated carbon provides superior adsorption capacity and longer bed life, making it a more robust option for long-term PFAS treatment. This slide presents the adsorption performance of PFHXS on 3 different activated carbons. The y-axis indicates PFHXS effluent concentration in ppt, while the x-axis shows simulated operational days. PFHXS, although a 6-carbon compound similar in chain length to PFHXA, belongs to the sulfonic acid group, which provides stronger adsorption affinity compared to carboxylic acids of the same length. As a result, the breakthrough times are longer than those observed for PFHXA. Among the tested carbons, reagglomerated coal-based carbon once again demonstrates the best retention, with delayed breakthrough and lower effluent levels. Directly activated carbon shows moderate performance, while coconut shell-based carbon exhibits the weakest adsorption capacity, with early breakthrough and higher effluent concentrations. This comparison underlines how functional groups, in addition to chain length, strongly influence PFAS adsorption. Sulfonates generally adsorb more strongly than carboxylates. This slide presents the adsorption performance of 3 activated carbons for PFOS removal. The y-axis represents PFOS effluent concentration in ppt, while the x-axis shows the simulated operational days. Compared with PFOA, PFOS demonstrates stronger adsorption due to its longer carbon chain and sulfonic acid functional group, which enhance hydrophobic interactions and affinity for activated carbon. Among the 3 carbons tested, reagglomerated bituminous coal carbon again shows the best performance, with the lowest effluent concentrations and the latest breakthrough. Directly activated carbon provides moderate retention but begins to show breakthrough earlier. Coconut shell-based carbon exhibits the poorest performance, with the fastest increase in effluent PFOS levels. Overall, this comparison highlights that PFOS, as a longer chain PFAS, is more effectively captured than shorter chain compounds, and that the type of activated carbon significantly influences removal efficiency. Here we present the key conclusions of the study. First, all PFAS compounds were removed by carbon treatment, but the performance varied among species. Lower molecular weight PFAS, such as PFBA, showed lower adsorption capacity and earlier breakthrough, while higher molecular weight PFAS were retained more effectively. The overall order was: PFBA is much less than PFHXA, less than PFBS, less than PFOA, less than PFHXS, less than PFOS. Regarding carbon types, reagglomerated bituminous coal-based carbon outperformed coconut-based and directly activated carbons. Moreover, both virgin and reactivated carbon proved to be viable treatment options, which highlights the potential for cost savings and sustainability in real-world applications. Thank you for your attention throughout this presentation. I hope it has provided clear insights into PFAS treatment using activated carbon. Please feel free to reach out with any questions, and don't forget to subscribe for future updates. See you next time.